Guess who's speaking at DDDPerth?
It's us!
Cool. That is good news as we're here.
Yep.
We want to thank our amazing sponsors, especially Microsoft.
Yes.
I mean, just kidding. All of the sponsors we want to thank, but especially Microsoft.
Yes.
We acknowledge the traditional custodians of the land, the Whadjuk people of the Noongar Nation.
As machine learning becomes increasingly integral to decisions that affect health, safety, economic well-being, and other aspects of our lives, it's important for us to be able to understand how model makes predictions and be able to explain the decisions based on those machine learning's decisions.
So this is not an advanced session. It's for anyone interested in exploring how we use data science and make predictions and explore what questions we can ask to validate how fair the machine learning model was in making those decisions.
We're going to explain the difference between global and local features importance. We'll use an explainer to interpret a model, and then we will visualize model explanations.
So there's a couple of things I always loop back to in developer conference talks: quantum physics and the meaning of life. And no need to worry, I am going to talk about both today. Because it occurred to me as I was rewriting this session for the 42nd time that if there was ever a tool to uncover the meaning of life, machine learning would be it. Humanity would use data science to take a peek into the inexplicable mysteries of the universe and find meaning in the unknown algorithms that govern the world that we live in. In fact, I'm not the first one to think of this. So Douglas Adams, in his epic The Hitchhiker's Guide to the Galaxy, wrote about a supercomputer designed to answer the ultimate question. Problem was, it told them it would take 7.5 million years to calculate the answer. So I guess they did not have scalable cloud computing at very affordable prices back in the day.
No.
So when the machine finally spat out the answer, the programmers were pretty annoyed because it made no sense without the context of the question. So they asked it for that. And it said it could not explain why the answer was 42. It built another computer to calculate the question and said it would be 10 million years before it came back with the questions. So the original machine learning model was a black box, and then it built an explainer model to try and calculate the reasons why the answer was 42. In this case, the explainer model was probably a PFI explainer model, and it built a mimic and then tried all the permutations of different questions to see which ones fit. And this is where it gets super meta. So when I started writing this session, I was thinking about how humans are the ultimate black box. We think they have reasons for doing what they do, and if we ask them, they can even explain them to you. But are they true? Are they correct? Do they follow a logic-based rule set, and do they spit out a consistent answer every time? Or do they have a little bit of chaos thrown in? Is there randomness in the pattern that makes us unpredictable?
Humans have a mental model of their environment that is updated when something unexpected happens. This update is performed by finding an explanation for the unexpected event. For example, Michelle feels unexpectedly sick and asks me, "Why do you feel so sick?" She learns that she gets sick every time when she eats noodle from that place around the corner. She updates her mental model and decides that that noodle place causes sickness and therefore should be avoided.
But those noodles are delicious.
Well, Michelle, you're gonna get sick. You're gonna keep getting sick if you keep going back.
Maybe not next time.
Possibly. So, when black box machine learning models are used in research, scientific findings remain completely hidden if the model only gives predictions without explanation. But as machine learning becomes very important to our lives, as I mentioned earlier, it's really important for us to be able to understand how model makes predictions and be able to explain the rationales behind those decisions.
So machine learning is a paradigm shift between normal programming, where all the instructions were explicitly given to the computer, and indirect programming that takes place by providing data. So when I was in university, I did philosophy, and we learnt about Schrodinger's cat. Did you know about Schrodinger's cat?
Now I know. 42 times.
So the idea is that you have a closed box with a cat inside, and there is no way to know whether the cat is dead or alive. Quantum physics tells us that there is a third state, that the cat is both dead and alive until the box is opened, and then it actualizes into one of those two initial states. But we aren't going to get quantum here because I definitely do not have enough credit on my Azure subscription for that.
I can borrow you some. No, I have to say I can lend you some.
Yes.
I'm still learning English, you see.
So let's treat this as binary classification. The cat is either dead or the cat is alive. And we could feed all the data that we have into a machine learning model to try and figure out which. So is the box airtight? Is the cat anxious by nature? Is there anything in the box with the cat? Poison, something sharp, a dog? How long has the cat been in the box? How big is the cat? How old is the cat? Is the cat sick? And all of this data is what we call features, or rather all of these data categories are what we call features. And if we had a couple of hundred boxes, all with cats in them, we would have a reasonable sample size to predict whether for one specific box the cat will be dead or alive. Now, of course, you are thinking that if we had all of those details about a specific box in front of us, then we could make a better prediction ourselves. I mean, dead, it would obviously be dead. But despite our original plan involving procuring hundreds of cats and hundreds of boxes...
I told you that wouldn't work.
Yeah, because budgets are always low in Q1.
That's not even the reason.
The storage space.
Possibly.
My point is supposed to be, data science isn't about small amounts of data. It's about taking lots of data, lots and lots of data, and making useful predictions or judgments from it. The bigger the sample size, the better the data. Probably.
So during COVID-19, there was a lot of data, more than 600 petaflops of data. And the fake news media like to spread the rumor that vaccines could not possibly have been tested to the same level as medicine were in the past. The truth is, they are tested in so many more iterations and variations today than could ever be possible in the past. In the past, we were limited by computer hardware. COVID-19 High Performance Computing Consortium brings together the federal government, industry, and academic leaders to provide access to the world's most powerful high-performance computing resources in support of COVID-19 research. How could vaccine not possibly be tested to the same level? Moreover, Duke University tested designs for multi-stitching devices for ventilators using over 500,000 compute hours over one weekend. In the past, that would have taken years to validate that data just for a trial. But by default, machine learnings pick up biases from the training data just the same as we do. This can turn your machine learning models into racists that discriminate against underrepresented group of people. Interpretability, therefore, is a useful debugging tool for detecting biases in machine learning models. It might happen that the machine learning model you have trained for automatic approval or rejections of created applications discriminates against a minority group of people that has been previously disenfranchised. Your main goal here is trying to grant loan only to the people that they will eventually repay the loan. But the incompleteness of the problem formulation in this case lies in the fact that you're not only wanting to minimize loan default, but also obliged not to discriminate on the basis of certain demographics.
So basically, you want to grant loans only to people who do not need loans, because they already have the money to pay back the loans, i.e. the rich people. But you aren't allowed to discriminate against people that traditionally do not have much money, i.e. the poor people.
Yeah. So data can be manipulated to support any conclusion, and such manipulation can sometimes happen unintentionally. As humans, we all have bias, and it's often difficult to consciously know when we are introducing bias into the data set. Guaranteeing fairness in AI and machine learning remains a complex social technical challenge, meaning that we can't only look at either social or technical perspective.
But what do we mean by unfairness? Well, unfairness encompasses negative impacts or harms, so for a group of people, such as those defined in terms of race, gender, age, disability status, or something else. Mm-hmm. So here's an example of fairness-related harms. Allocation. So, for example, if a gender or ethnicity is favoured one over another. An example of this was an experimental hiring tool developed by a large corporation to screen candidates. They were aware that there was a large number of one gender over another in their workplace, and they assumed that the first line interviews being done by humans were introducing that bias, and so it would be better to take those out of the loop and have it all the CVs scanned by a machine, and it could spit out which was the better candidate. However, they trained those models on the previously successful and unsuccessful CVs, and the machine learning model assumed that it was particular words that were the success factor or the failure factor, rather than judging on qualifications, experience, and everything else that was expected.
Another example of the fairness-related harm is quality of service. If you train the data for one specific scenario, but the reality is much more complex and you have not taken that into considerations, it leads to poor performing service. A notorious example was an automated hand soap dispenser that could not seem to be able to sense people with dark skin.
So it's really important that you don't just use white men in your data set. There are other people in the world. Women and children are generally smaller and lighter. There is a range of skin colours, accents, abilities. And although it's super easy to make that first test on your internal team, if you aren't seeing a lot of diversity in them, then that data set will not be truly representative, and it might lead to bad results, sometimes even deaths. Like with the airbags, when those were initially invented, those were tested by the men that were building the cars and the airbags. And when that went live into the real world, a lot of children and women died in those first car crashes because the force which the bag explodes at was too much for their slighter frames. Mm-hmm. So you see, bias in many data sets might come from unbalanced data or lack of retraining on those features. Machine learning models can only be debugged and audited when they can be interpreted. So even in low-risk environments, such as movie recommendations, the ability to interpret is valuable in research and development, as well as after deployment. See, we always start laughing in that bit because that I'm furious, because that should be an easy one. My movie streaming provider of choice should know never to put Jeremy Clarkson in my recommendations, and I don't want to see any reality TV shows. There is no reason for it to do that.
Love Island.
But you see how mad I get, and it's just about movies. Imagine it was something that had actual impact on my life, like in a legal sense or a financial sense or a health sense. So an interpretation for an erroneous prediction helps us to understand the cause of the error, and it delivers us a direction to fix the system.
So there are a lot of domains that would benefit from these understandable models: health, finance, law, and there are even more that demand this interpretability. Being able to audit the model for these critical domains is very important. People need to believe that computers are fair. People need to believe computer first and believe that it's are fair.
Fairer than us. Fairer than the humans that
designed them. Exactly.
Yeah, we are very unfair on the bots. So, understanding the most important features of a model gives us insights into the inner workings and gives us directions for improving the performance and removing bias. Why don't you show us how to create a model, Gia, and then we'll talk about the features after that.
Sure, Michelle. So before we actually go into this interpretability creation of the model, we need to have the working model first. So in this demo, I am creating a simple binary classification model using logistic regressions, using student hiring dataset. Imagine that your boss telling you to create a machine learning system to screen out the student candidates based on the historical hiring data for the grad program. And it includes their GitHub contribution score, their marks at uni, number of hackathons, and number of volunteering activities. The first thing that we need to do is to install required packages, including interpretability, community, and RAI widgets. You can see that I am loading that without any errors. Now, let's move on to loading the dataset. So I load the dataset using Panda library, using this library to separate features and labels, and also splitting data into training set and test set. I think it's 70-30 using train test split function from sklearn library. You can see the output, which is gonna come in a minute.
He's not looking at us, so us dabbing makes no difference.
Oh, okay. I was dapping in the background because I leave this awkward blank moment. Okay, so you can see the output of when I load the data set, and there are 4 features. One label column at the end, and 1 is hired and 0 is not hired. Next, now that we load the data set, we create a classification model which makes a decision whether a student candidate will be a good fit or not. We use logistic regression from scikit-learn, and we see how the model performs by calculating different metrics such as accuracy, area under curve, precisions, recall, and F-score. Now, honestly, the moment that you see the output, it is not the best performing model because the accuracy is only 60%. I am still learning how to create the model and play around with the hyperparameters, but we will keep pushing on. We use this model for creating the interpretability for the black box because this is what we focus on this session.
I mean, I wouldn't worry about the 60% because, you know, if we were really going to use this model, then we would find it a lot more data, and we would work on, refining the feature importance and stuff like that a lot more. I mean, this is good for a first run.
Absolutely. Cool. So I think that was it. That was the demo for creating the model.
Yeah, so we didn't really introduce ourselves. And here we are well into our session.
That's true, Michelle.
So we're going to talk about features, global features and local features and feature importance.
I see that you put the data set of me on the slides.
Yeah, and there are some entries that are missing there.
Ah, okay. The one in white would be the features normally quantified as most important in influencing the judgment or prediction in a data set. We call those the global features.
So why don't you tell us the data for those features?
My name is Jiaranai Keatnuxsuo. I am an associate class solution architect and I work at Microsoft.
And why do you think those features had priority in the data set?
That's what people want to know when they first meet you, your name, what you do, who you do it for. People judge you based on those things first, and then they might want to dive into other things like my weight.
Nobody wants to know that.
But you put weight up on the slides.
It's an insignificant feature.
Okay, Michelle, what about you? In your case, those things are not the most important features.
Exactly. I always said I was a community advocate even when I was working as a service delivery manager, because although SDM was the job title I had, it didn't describe who I was.
And there is some data missing from your data set too.
Yeah. Well, it's not significant for anything that I want to do with my life. If those features took on a higher weight, it would definitely reflect bias in the data set.
I see. So when different features have different priority in a particular instance from what is globally perceived to be important, we call that local features importance.
You got it.
Yes.
So global feature importance quantifies the relative importance of each feature in the test data set as a whole, and it provides a general comparison of the extent to which each feature in the data set influences prediction.
For example, a binary classification model like the one I used just now to predict if a candidate will be a good hire or not, an explainer might then use a sufficiently representative of the test data set to produce global features importance values. It could then show that the model was trained from features such as qualification, experience, previous tenure, and skills to predict a level of 1 for candidates that are likely to be good hires and 0 for candidates that have significant risk of failure in the role and therefore should not be approved or hired.
So when we hired Gia, though, a completely different set of features weighed higher in the process. This was because Gia was hired under the graduate recruitment scheme rather than the professional pathway. So we didn't expect her to be able to show a long tenure in previous roles or have experience working at Microsoft partners or have a multitude of recommendations. In the grad hire route, the feature with the highest importance is her degree. She needs to be a graduate or she cannot qualify for that hiring route. Her awards, volunteering experience, and GitHub portfolio might be heavily weighted features as well. And this is what we call local feature importance. In the overall data set, these things do not have the highest weighting, but in a run looking at grad hires, these features are given more weight. Or I should say, specifically in Gia's case, these were the features that held the most weight.
So you can apply the interpretability classes and methods to understand the model's global behavior or specific predictions. The former is called global explanation, and the latter is called local explanation.
The methods can also be categorized based on whether the model is whether the method is model agnostic or model specific. So some methods target certain types of models, for example, Shap's tree explainer, and only applies to tree-based models, and some methods treat the model as a black box, such as the Mimic Explainer or Shap's Kernel Explainer. Why don't you show them, Gia?
Sure, Michelle. Bring it on. All right, so it's easy to create the explainer for the model. We use the interpretability library that we installed earlier. And if the demo is going to run, it is running. Cool. So the explainer will calculate the features importance for us, which enable us to quantify the relative influence each feature has in predicting whether a student candidate will be a good fit to the role or not. We will use a Tableau Explainer, which is a black box explainer. And the cool thing about this is that Tableau Explainer look at the type of the prediction model, and it will decide for us what is the appropriate explainer. Now, the output will come in a minute once I run this code. Are you capturing me? Okay, you cannot see me dapping, but I am dapping. while I'm waiting for my output to come up. So, okay, the output, it will show it will show that the Tableau Explainer called Linear Explainer. There you go. Remember that we were using logistic regression model for our prediction, and Linear Explainer is actually the appropriate explainer for the logistic regression. Now, once we have initiated the explainer, we want to try to explain the model by evaluating the overall features importance, or what we also call global features importance. This means that it look at the whole data set, and we call explain_global method on the explainer we created. Then we'll use get_feature_importance dictionary to get result from importance values. And the features is ranked with the most important feature listed first. Now you can see the output here is that hackathon comes first, and then it's the mark at the university, and then the GitHub project, and then volunteering activities. Now, once we have the overall view of the global importance, what about the explaining individual observation? This is where we need local features importance. It measured the influence of the feature for a specific individual prediction. In other words, it's only look at one single candidate. So to get the local features importance, we call explain_local method, and specifying the subset of the case that we want to explain. In this case, I just want to look at the first candidate. And then we also call get rank local names, and then get rank local values to get the feature names and importance values for these local features importance. Now, let's look at the output. There's a lot of things going on there. Since this is a binary classification model, there are only two possible classes, hired and not hired, right? Each feature support for one class results in correlatively negative level of support for the other. For this candidate, let's say this is Jia, right? Jia overall support for class 0, which is not hired, is minus 0.95. And the support for class 1, hired, is correspondingly 0.95. So support for class 1 is actually higher than support for class 0. This means that Jia is a good candidate will be a good fit to the role. So the most important features for the prediction of class 1 is the number of hackathon that she participated in, followed by GitHub score. And remember, these are quite different than the global features importance value. In the global features importance value, it was hackathon and then followed by marks at university. But there might be multiple reasons why local features importance and global features importance value differ. It might means that Jia might have a lower marks than the average compared to other students, but she's still a good fit because company cares about her hands-on experience with hackathons and contribution to the GitHub project. And there we have it, Michelle.
Good.
It's easy, right, to create an explainer.
So earlier I was talking about the computer in the Hitchhiker's Guide to the Galaxy, and how it created a mimic model with a PFI explainer to interpret what the questions was. This technique can be compared to a child learning to annoy their parents. So the child starts with no preconceptions as to what makes their parent angry, and then they can test their parent by picking a random set of actions over the course of a week and noting how their parent responds to those actions. So while a parent may exhibit a non-binary response for each of these, let's pretend that the child's actions are either bad or good, two classes. And so after the first week, the child has learned quite a bit about what bothers their parents and makes an educated guess as to what else would bother their parents. So in the next week, the child doubles down on those actions that were annoying and takes even more that it thinks will really push its parents over the edge.
Testing the boundary.
Exactly it. So the child repeats this each week, noting their parents' responses and adjusting their understanding of what will bother their parents until they know exactly what annoys them and what doesn't. The augmented data is labelled by the black box model and used to train a better substitute model. So just like with the child, the substitute model gets a more precise understanding as to where the black box's model's decision boundaries are. And after a few iterations of this, the substitute model shares almost exactly the same decision boundaries as the black box model.
So it would help if we visualize the result from our explanation. Remember that local features importance split out a lot of things in the Jupyter Notebook cell. Reading from the result from that cell can be difficult, and we can have a simpler way to visualize the explainer by using the responsible AI widgets. This package will provide a collections of model and data explorations and assessment in a nice user interface way that enable a better understanding of the AI and ML systems. We call the explanation dashboard on our previously defined global explainer and prediction model. Remember, it was the logistic regression. And then we will see the dashboard pops up. There you go. The dashboard is there, and if this is too small, which is too small for me, I follow the generated link on my compute instance that is being hosted on Azure to see a fuller dashboard. Now, if you go to the third tab, aggregate feature importance, that will give you the interface for interactive visualization of the global features importance. And if you go to the last tab, individual features importance and what if, it will give you the visualization of the local features importance. And if you click on the individual data points, you can see how the explainer results change. You can play around with it, and you can play around with these visualizations however you like. The dashboard will give you so much flexibility that helps enhance the understanding of the model interpretability. And that's it, Michelle. Visualizing the results. Yep, I'm still keep going.
Seems to be still going, Gia.
Yep, they're still going. There's so much to show, right?
So earlier I was speaking about the computer in the Hitchhiker's Guide to the Galaxy and how it created a mimic model with a PFI explainer to interpret what the question was. Wait. Oh, sorry. I've already done that. I feel like, you have a sense of deja vu. Here we go. So, it's become quite common in these days to hear people refer to modern machine learning systems as black boxes, but in many cases they are not. It just seems like they are because they are like people, complicated.
Mm-hmm.
So when we ask someone why they did something, we're operating on a certain set of assumptions. We're typically assuming that they had some good reason for acting as they did, and we are basically asking for the reasoning process that they used to make that decision. However, when we're asking why something went wrong, we are instead asking for some kind of root cause analysis of the failure. For example, after a bike accident, we might want an explanation of what caused the accident. Was Gia distracted? Did another rider swerve into her? Was she drunk?
No, I was not.
Rather than a process of reasoning, we're asking more or less for the critical stimulus that caused this particular reaction outside of normal behaviour.
I thought that was normal.
There's a separate scale for Gia. So with machine learning models, you can choose to elevate certain features above others, salary and existing debt in a loan approval tool, for example, or certain features might rise to prominence through training. I've been training the Azure Percept Lego car to avoid cones, but I haven't trained it to avoid Lego people. So it would definitely just mow those people down unless it mistook them for cones. But why did it mow down the people? It wasn't a decision that the Percept car made that, Lego people are more evil than cones, because obviously they are more evil than cones.
Obviously.
It's simply that it doesn't recognise Lego people as anything valuable at all. So the purpose of this session was to show you that despite the fact that one, at least in part, created the other, we're not so different. machine learning models can be interpreted, and there are many models and many ways to gain insight into what they're doing, possibly more than we have to tackle humanity as individual decision makers.
So, Michelle, what's next?
So we have a whole bunch of learning paths here. This is the one that Gia and I followed in order to understand the black box models and explainer models. So if you want to do what we have done, follow this one here. There's also like a bunch of free learning resources on Microsoft Learn. If you want to know how to be a data scientist, a data engineer, an AI engineer, a business analyst, I cannot even remember all of the learning paths that there are there. There's really a lot. There is something for everyone. So check those out on Microsoft Learn. Those are all free, and a lot of them lead to certifications, which are the part you need to pay for, but it's only like $100. And if you're a student, it's only $15. There's also a bunch of learning that has been created by the Azure Cloud Advocates. So if you want to learn about machine learning, we also followed this one for this course. There is a IoT one. There is a web programming one, Web Dev for Beginners, which I need to do that one as well, because my coding is not as good as it could be.
Well, we can only improve on it.
Yeah. And if you would like to join the community, then that would be really awesome. You will get access to more webinars, more free training, more interesting events that you can come to, and potentially free swag. Thanks for listening to us today.
Thank you. Goodbye.